Okay guys, I have a new video about the Echo Designer tool and the filter section on the SNES. It turns out that the filter section tool on the SNES was a lot more powerful than I thought it was. And so I updated the Echo Designer tool to take advantage of those new capabilities, and I want to explain those capabilities to you. So we're just going to jump in. Okay, so let me draw out the filter section of the SNES to give you guys a better idea of what's going on. It starts out with the signal coming in here, and it's added to something. We're not going to show what it's added to quite yet. Then it passes through a delay by 1 unit of time. We're leaving that D. And then it goes to a fur section. So I'm just going to label that fur for now. The fur passes through here, and then it gets multiplied by a value that we're going to call F. And then that value is added back to the input signal. Okay, so originally when I designed the Echo Designer tool, I was basically showing the output at this point, which we're going to call uppercase E. But it's not quite that simple. There's more going on here. So this output E is multiplied by a value, and the output of that multiplier is added to the output of another multiplier, and the input to that other multiplier is actually X as well. And so here we're going to call this uppercase Y, and that's the full filter section. That's basically all of the math being done, or all of the operations being done to the input signal. Okay, so we're going to call this multiplier, the value here, we're going to call that V underscore E. We're going to call this V underscore M. This signal here is uppercase E. This is a delay. And this delay will represent that, we'll call that Z negative 1, because we're going to work in the Z transform space. This multiplier is F. This F is kind of messed up. So given this diagram, we're going to derive the full transfer equation. And before we derive the full transfer equation, I want to talk about this fur filter section. So in the last video, or in the last video we did when we talked about the fur filters, we kind of gave these transfer equation of H of Z. And so this H of Z for the fur filter, if you remember, it was B0 plus B1 Z negative 1 plus B2 Z negative 2 plus dot 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 Bn Z negative n, right? Okay, so if we understand this, we're just going to use H of Z as a placeholder for the fur filter. Okay, so now that we know that, let's derive the transfer function for the entire filter section. But we're first going to start by trying to derive the transfer function for E. Okay, so we'll just start out very simply. We'll say that E times F plus X now we multiply that by Z negative 1, because that goes out through here. And then we're going to multiply that by this H of Z, because this H of Z is the effect of the fur filter. And then all of that equals E again. Okay, so we can, we'll distribute the Z negative 1 and H of Z. Distribute to the E plus F term, or E times F term. That all equals E still. We'll move this E to that side. And we'll factor out the e here. This side stays the same. Then we'll divide this side by 1 minus f times z to the negative 1 times h of z. So then if we do that, I'm just reversing the sides here, we get e equals x z negative 1 h of z. Let me move this down. Divided by 1 minus f z negative 1 h of z. Okay, so we'll divide both sides by x. I'll just delete that x here. Okay, and we'll say that e over x equals this. And so e over x is the transfer function from x to e. And it equals this. And so this transfer function was originally what the tool was computing in the original tool. But like I said, it turns out we have this effect here. We have what's going on over here as well. So e is passing through this, x is getting added there, and we get this y, this actual output y. So if I block this off, I can show that y is actually e times v of e plus x times vm equals y. So I have an expression for e. X is just the input signal. I know v and I know v of m. So I can actually expand this to get a full transfer function for y. So let me do that on the other side. First, I'm going to copy this. So I just know what I'm working with here. So I'm going to copy this to this side. And I'm going to copy this as well. So I have both. Okay. So let's do this. So I'm going to say, I'm going to replace e here with this. Multiplied by x because I just want e. So z to the negative 1, h of z times x. All divided by 1 minus f z to the negative 1 h of z. Multiply that by ve plus x vm equals y. And so I want to get this, I want to add this term up here. The way I can do that is I can multiply both the top and the bottom of this term by this denominator, so they both have the same denominators. So I'm just going to keep that the same. Actually, no. I'll write this entire thing out again. H of z x all divided by 1 minus f z negative 1 h of z. And so then I'm going to multiply x times, oh, actually this is all multiplied by v of e. I'm going to multiply x times v of m times this. So then we have x vm 1 minus f z negative 1 h of z equals y. Okay, so now I have to simplify this top. So what I want to do is I want to collect all the terms that have h of z together. So wait, well first let me distribute. So I'm going to distribute v of e across here and then x v of m across there. So I'm going to have x z negative 1 h of z v of e plus x v of m times 1. No, I actually don't need the 1 there. And then minus x v m f z negative 1 h of z equals y, and that's all over 1 minus f. Actually, let me fix that. That line's kind of crazy. 1 minus f z negative 1 h of z. So let me simplify this. The way I'm going to do that is I can factor x out of all of these. There's one x term on all these terms. And I can merge these two together, and this term is by itself. So I'll say x multiplied by v of m. That's this term. And then I have these two. So these are basically, this is z negative 1 h of z times ve. This is z negative 1 h of z vmf. So I can say that that's VE, so that's this, VE minus VMF. Multiply that by z negative 1, h of z. All of that is 1 minus f, z negative 1, h of z equals y. Okay, so we're basically there. So now I just divide both sides by x. And then I get the transfer function from x to y. So this is basically just exactly the same thing that I wrote. Y over x. And this y over x, I'll call it h2. h2z. Okay, and so this is actually the this is the full transfer function of the entire echo section. And so there are kind of, so when I derived this, a few things popped out at me at first. So the first thing that popped out at me is that if you set this part, v of e times v of m to f to 0, if you set ve, vm, vf such that this equals 0, then you cancel all of the zeros of the transfer function. And so then you're just left with vm over 1 minus f to z negative 1 times h of z. And so the only active components of the transfer function, so to speak, are the poles. So you're able to then create pole-only filters with the SNES. And so this is a big deal, and I'm gonna go into why this is a big deal later, but this is huge. The other thing that I noticed is that now that you added this v to the m term here, and you multiplied the z negative 1 times h of z here, that gives you an extra 0. So before we were working with 8 zeros, we actually have 9 zeros to work with, and this allows us to build better, more steep filters. And so if you set f to 0, then you get no poles. So you can create filters with 9 zeros and no poles. That's great. And so the last thing I noticed, you have this constant times a multiple of z to the negative 1 times h of z. Same thing on the bottom. You have a constant, which is 1 in this case, times a multiple of z to the negative 1 times h of z. And so that shows us that we have at our disposal the ability to create filters with the same amount of zeros and poles, period. And at first blush, that may not be significant, but it turns out that when you're converting filters from continuous space to digital space or discrete space, the conversion often results in a discrete filter that has the same amount of poles and zeros. So that's huge, and that's also what was limiting me when I was trying to create filter generators in the past. So we actually have, so those 3 new capabilities are huge for creating filters with the SNES. 1, we can create pole-only filters. 2, we actually have 9 zeros instead of 8 zeros. And 3, we can create filters that have the same amount of zeros and poles, which is huge. So with that new knowledge of the transfer function of the filter section of the SNES, I've updated the Echo Designer tool. And so I'll show that here. It may not be obvious at first, but you can see that now I have 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Whereas the tool before was only showing 7 zeros. Now you have 8 zeros. to work with. And of course it works all the same. And so the tool, when you move around the zeros, it's been set so it doesn't change your master volume. And this is important because now you can have voices playing on the normal side with echo disabled. And if you're manipulating the filter, they're not going to get, you're not going to hear changes in the volume as you play with the filter. Those changes, the filter changes are only going to affect the voices that have echo enabled. So that's great. And that's actually, that actually addresses a big deficiency in the tool before where you had to set the master volume to 0. That just doesn't really work when you're like actually making music with SNES. And so the other changes that I've made are that the bandpass filter, like I said, now generates bandpass filters with 8 zeros. So let me set there, and there's 2 modes to this. There's a preserve master volume mode, and there's a mode where it doesn't preserve the master volume mode. So I'm going to go into the mode where it doesn't preserve the master volume. And you can see now I have 8 zeros in my filter. And then this just gives us a marginally better filter. It's not the biggest change ever, but it's just a marginal increase in filter quality. Now the filter's a little bit more steep. It's not as broad. So this filter width we get a better cutoff with that. But there's now this other mode called preserve master volume. And the whole point of that is, like I said earlier, maybe you have something playing on the master track and you don't want that being changed as you manipulate the filter. So you can set this preserve master volume setting and you can change the center frequency, and it's going to leave the master volume alone, and it's only changing the sound that's affected by the filter section. So that's good. You can manipulate the bandpass filter and it has no effect on the voices that don't have echo enabled. It only affects the voices where you have that echo enabled and you actually want, some filtering going on. The other change is that I've changed the feedback-based bandpass filter a lot more. And the reason is because previously it was mandatory to have a 0 when I was trying to create a filter with poles. And this 0 really complicated the design of the filter. I can't get into all the specifics, but because you have a 0, because you have a mandatory 0, it's changing the magnitude response that you're looking for. You might want a certain magnitude response by placing poles in a certain place, but then if you have a 0 that's kind of popping out that you can't really, that you have to kind of like deal with, that 0 may warp your desired magnitude response. But now we can create filters without zeros with only poles. So it gave me the opportunity to make this feedback-based bandpass filter a lot better. Because now that it's simpler to design without these sort of like confounding zeros, I can control the output response that I want a lot better. So I'll just show you that here. So when you set resonance to 0, you're not really seeing that much of a change. Well, you are seeing a change in the shape of the magnitude response, but you still get that very subtle, I don't know if you remember from the last video, the effect was a very subtle effect. Here I'm seeing about 8 decibels in difference between the peak and the lowest point. The bigger change is when you set the resonance all the way up. Now I'm able to put the pole right up to the unit circle across the entire frequency spectrum, not just in the middle like I was doing in the last video. Now the pole can be right up to the unit circle across the entire frequency spectrum, giving us a very strong resonance across the entire frequency spectrum. So I don't know if you can see that. And so this is really good because you now have the ability to kind of like very specifically pick certain frequencies that you want to amplify across the frequency spectrum. And with this, you can actually do a sort of subtractive synthesis if you're passing in a harmonically rich sound source. Using this feedback-based bandpass filter and cranking the resonance all the way up, you can always select a very specific frequency from that harmonically rich sound source, and that allows you to do a sort of like subtractive synthesis. So I'll show a little demo of that. So what I've been doing is my demo, I've just been using the noise, the internal noise generator of the SNES. Okay, so if I turn that noise, let me turn the volume down just a little bit. I don't blow your guys' ears out. Okay. So if I turn the noise on, so you can see that as the noise is just on, the noise is like harmonically rich, has frequency components all across the frequency spectrum. As I move the center frequency of the feedback-based bandpass filter, you can hear the specific frequency components being amplified. And so you can create a subtractive synth that way. And so I brought this up on the Discord, and some people brought up other ideas using the filter section of the SNES to also synthesize sound, which is pretty cool. So another thing you can do is that we're using stable resonance. And stable resonance is basically when the poles are within the unit circle. So I'll demonstrate that again. So generally with filters, you want your resonance to be stable. You don't want your poles to be outside the unit circle, because when the poles are outside the unit circle, basically the signal never dies in the feedback path, and it eventually will cause distortion, and it just doesn't work. But you can actually exploit infinite resonance to synthesize sounds with the SNES. And the reason this works is a little bit involved, but I'll just show you guys. I'll show you guys how it works just so you can see. Okay, so you can see here that I have one pole outside the unit circle. And so what does that sound like? So in that example, as the magnitude of the pole increases, the pitch of the synthesized sound increases as well. And as the magnitude of the pole decreases, the pitch of the synthesized sound decreases. This is not supposed to be possible. It's exploiting sort of like the brokenness of the SNES to get that effect. When I first heard this, I was totally blown away, because the idea of exploiting instability to get a synthesized sound was just something that was just completely not on my radar. But after a few hours analyzing this and looking, obsessively trying to understand how this was possible, it kind of fully made sense. The explanation is a bit complicated, and maybe I'll write like a little article to explain it more fully for people who are curious. It's pretty cool, and I mean, in some instances, you may actually want to do something like this. So I want to give credit to Kung Fu Furby from the Discord. He's also on Twitter, and he shared this effect with us on the Discord. So credit to him. So if you're interested in this stuff and you know of any other ways to exploit this hardware to get interesting sounds, please join our Discord, or message me or comment below. I'm genuinely intrigued by what you can do with this old hardware. So yeah, if you have any other information, please let me know. For me, retro hardware is a less intimidating way to learn advanced technical subjects. And if we can breathe new life into SNES music at the same time, it's a win-win. In the past few videos, I've been going more over the advanced settings in the filter section of the SNES hardware. In future videos, I want to kind of take a step back and go over more of like the basics of SNES sound production and make the videos a lot shorter. For instance, I want to give more of a kind of like 0 to 100 tutorial of the Echo hardware, because there's a lot of stuff I haven't covered, even in this video series, that are actually pretty cool usages of the Echo hardware. In future videos, I'm going to be going over that. So if you want to see more of that, if you like this video, please comment, like, subscribe, and all that good stuff. And I will see you in a future video. Bye-bye.